So no, we are not yet to the code part. Just give me 2 more minutes and I'll explain the mathematics that we are going to apply so as to get the same formula converted to code. So since in the very beginning we understood that we are going to be getting values of x and y in tabular form, so let's just say we get it in a matrix form such that x1 to xn for the first value, then dot 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 x1 to xn for the mth value or the mth index. So we have a total of m instances, right? So we have n instances. For each instance we have a corresponding y. So we have y1 to ym. So let's call this table A, and then let's call this y. So what we understood last time is that for a given value, for all these values, if we go ahead and multiply them with respective values of m, we can find y, right? So if I go ahead and say that there's another matrix which is w, here w, so yeah, if it's w and we multiply a with w, we will get y. So let's see what is going underneath. So for a given instance, x1 will get multiplied with let's just say m1, then we have x2 which gets multiplied with m2, and so on and so on, and this will become y, and somewhere we'll have our intercept c, and since we are ignoring c, let's say that c is 0. So the simpler problem that we saw previously, we only had x into m plus c. Now we have x1, we have x2, we have xn till xn, right? So this is the basic difference between linear simple regression and linear multiple regression. In simple regression we only have one variable on which y depends. So if we have only one variable x on which y will depend, this is simple linear regression. And if we have a set of values x1, x2 and so on which y exists, this is known as multiple linear regression, right? So now we know the difference between simple linear and multiple linear regression. So yeah, let's get back to AW is equal to y. So this was our equation. Now we understand how this becomes translated into a matrix form. So we can actually work with matrices in code, so that's why we keep a track of this so that we can convert it back to a matrix and then we get the value or get the calculation in a better way. So now we have AW is equal to y, AW is equal to y. So now again we have our error function. This time our error function will look something like this. So we have y predicted transpose dot y, then y predicted. So this will actually become our error function, and if we go ahead and using this error function try to find a value for w, because what w basically contains all the values m1, m2 dot 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 mn. So if just to give you an intuition, so A contained x1 to xn and had m instances, so the shape was m into n, right? Now this contains n instances and has one column, so this is basically n into 1. So if you know the basics of matrix multiplication, if you dot product these two matrices, then you get a matrix of shape m cross 1, right? So what is this m cross 1 matrix? This again is the this again is y1, y2 dot 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 ym, right? Makes a little sense. So now since we saw how we use this error function to find the value of w, or all the values of m1 to mn in such a way that this error function is minimized, we aren't going to again take a dive at all these things again. We'll just write the equation directly. So our W will become equal to A transpose dot product with A, and we'll find the inverse of this. Then we'll again go ahead A transpose and then again a dot product Y, right? So this formula is what is used for the gradient descent process, and to find the weight or the value W, which contains all the values m1 to mn in such a way that the error function is minimized. So right now we don't actually have to worry about the learning rate and all these things but it will come in your way sooner or later, right? So now we have the formula, we have some data that we are going to be working with. So let's go ahead and move ourselves to code and see how this is applied in code. So let's start with importing some libraries. Again, we import NumPy and Pandas as usual, Cbond as usual, you know all these things already. So a new library, sklearn. So not very big operations as of now, but for now we are going to be using sklearn for uh, making splits. So again, we split our data in such a way that we have two parts. On one part we'll make our model see that part and start to learn, and then to test our model we'll use the another part known as the test split, right? So it's like notebook and exam. So our notebook is the train set in which we have all the information which we are going to give the model or give the student to keep on learning, and after he has learned we'll give it a test. So if it has learned or not, giving the new data, so we'll teach it 3 plus 4, 4 plus 5, 5 plus 6, something like that, and then we'll ask it 10 plus 11. Sounds like Indian education system? Well, yeah. So now after that we are going to compare our model, that formula that we are going to be using with the inbuilt linear regression model. So yeah, a lot of the libraries come with the inbuilt model so that you don't have to actually implement them from scratch. So we'll see something called as one hot encoder for categorical data, since we are going to be dealing with categorical data, and even though we are solving a linear regression or regression problem in general. And yeah, so this is the data. Let's take a look. So our data has this feature variance, then skew, then kurtosis, something like that, and entropy. So all these features are there, and then we have the class. So we have to predict class given all these input features, right? So let's take a look at the information regarding that data. So I don't think we have to perform much pre-processing on this data, because there are no null values, all the values seem to be there, and the data is fairly simple. So what we'll do is that we'll keep this data going, and we'll show the performance of different models on the same data, so as to get a better understanding that how models are working to keep on the same scale, to stay on the same scale of the same data. So now let's see how many different values of classes are there. So there are two values, 0 and 1, and there are 763 instances where the value is 0 and 610 instances where the value is 1. So what do these represent? These actually represent if the bank note or the note from the bank is real or not. So 0 basically represents that the note is forged or note is not real, whereas 1 represents that the note is real. So not too much, but let's just go ahead. So if we just take a look at how class is dependent on variance, skewness, kurtosis or whatever, and entropy, we can see that there are polarizing results. Why is this so? Well, it's just because of the fact that there are just two categories in which they can be classified. Either class is going to be 1 or class is going to be 0, whatever the value of variance, skewness and all these things are, right? So now what we want to do is we'll perform a very basic pre-processing. So now we'll go ahead. So now we'll go ahead and perform a very basic pre-processing. What we'll do, we'll start by splitting the data. So this data is basically the input data, and then this class is basically the output that we are going to be predicting. So we split the data, then we find the number of classes and then convert this value of output y or class into one hot encoding. So let's go ahead and see what one hot encoding looks like. So it's 1 0 1 0 and later it becomes 0 1. Doesn't make sense. Well, one hot encoding, for example, if we have a value in range, for example, if we have values for like 1 2 5 6 something like that, so what one hot encoding will do, it will change all these values in relative terms. So for example, if we have the range is from 1 to 8, so we have one hot encoding vector of 8 different values of zeros. So 1 2 3 4 5 6 7 and 8, right? So if the value is 1, what will happen? The value at position 1 will become 1 and rest will become 0. If the value is 2, the value at position 2 will become 1, rest will become 0. If the value is 6, so 1 2 3 4 5 and 6, the sixth position will become 1 and rest will become 0. So why do we actually convert it in such a way? Because if they are plain categories and they don't have an ordinal relationship with each other, means we have already well discussed ordinal relation, but if again ordinal relation is the kind of categorical data which has relation among them. So like increasing values or decreasing values are ordinal values, but if they don't have an ordinal relation, then that doesn't makes any sense for us to keep it that way, and it will basically become an hindrance in the entire process. So yeah, we convert them into one hot encoding vectors. So now just a very basic scaling of data. So we have already discussed what scaling is, so if you are not familiar with it, just go back and revise once. So we just scale the data. Now we are splitting the data into training part, train X and train Y. This is what our model will train on, and then we will have text X and text Y. So just to feed the model after learning this value X and get the prediction Y prediction and test it against the value of test Y. So now the model. So since we are familiar with this notion now, what we'll do is we'll just change okay, sorry, I forgot to done this. Then yeah, so now if we go ahead and take a look, these are all the instances. So we have 10 data about 1097 nodes, and for each node we have 4 values. The values are variance, skewness, this and this, right? And for each banknote we now have for all the 1097 banknotes we have 2 values. What are those 2 values? Well, these 2 values. So if the 0th position is 1 or 0th position is hot or lit, then the category is 0, and if the 1 position is hot like this and the 0th position is 0, then the category is 1. So we had 2 categories, 1 and 0. Now we know how they are represented. So that's why the shape of y is for all the instances, each instance will have 2 values, right? So now the actual formula, this formula, how it actually converts into code. So this formula, what we first do is we find A transpose, this A transpose, and find the dot with A. So this gives us, so let's go ahead and do one thing. Split it in a good way so that it's more readable. Then what we do, we find the inverse of this. So we find this value a raised to power t, sorry, A transpose into A or dot A, then we find its inverse. After that, what we do is we then again go ahead and find the dot with A transpose, and then again we dot it with y. So now this, we know how this formula is again implemented in code. Now we just go ahead and find value of y. Now let's take a look at the value of y. So y is basically 4 cross 2 matrix. Why? Because this is 4, this is 2, right? So if we multiply a matrix of 4 comma 2 with matrix of shape this, then we'll get an output of shape this, as we just saw. So now let's go ahead and test our model. So we find the predictions using the formula, this formula, y is equal to a dot w. So text x dot w, we find y prediction. Now we again have to convert y prediction from this kind of value to this, just 0 1. So now we convert it back, and let's take a look at the change of shape. From 2 it became again 1, or nothing is there, which means it's 1, basically 1. So now we again have zeros and ones rather than the one hot encoding vector. Now to evaluate, what we'll do is we'll just plot a confusion matrix. So confusion matrix basically says that here if we are having true values and then false values, that for y, and then we have the true values and false values for y prediction here, right, column wise and row wise, then the values on the diagonals are good predictions, or the predictions that became true. So for example, in this case we had two classes, 0 and 1. So real 0 and real 1, and this was the predicted 0 and predicted 1. So real 0, which was predicted as 0, is 139, means 139 instances were as such that were 0 in actuality and were predicted 0. But 6 of them, which were actually 0 because rows represent actual value, but were predicted as ones because column represent the predicted value. So we don't want this, right? So we have a model that learned well enough to predict 139 nodes as 0 because they were 0, but failed to predict 6 of the nodes. Now the another going ahead, the nodes that were actually of class 1 and were classified as class 1 are 130, and there was no node that was classified as class 0 even though it was class 1, right? So these are the diagonal values, are the true values that we want to maximize, and the non-diagonal values, or let's just say any other value other than the diagonal values, are basically something that we want to minimize. So we now know the performance, so we can go ahead and just see how accurate this was. Oh, okay, I did the wrong so we have 139, then add it with 130, then divide it with this plus 6. So currently our model is 97% accurate from the data that we have, right, from the values that we get. So now let's use the library function rather and see how it performs. So just importing the library function linear regression, so it's not function, it's a class. Then we again train it on the input data train x and train y, so training data, and then we find a prediction again. Then we again go ahead and plot the confusion matrix. So this seemed to have a better performance because like last time we have 130 for class 1 and we had 139, but here now we have 142. So now if I go ahead and check for the accuracy, so it returns 142 plus 130 divided by this plus 3. So now the model is 98% accurate. So yeah, sometimes the very basic mathematical version would work better, but sometimes this one will the library function will work better. So the very basic reason is that it's written by smart people, let's just say, and they know their thing, so they have written it in a way that it would perform good, right? So that's why we tend to use library functions over this. But yeah, knowing the basic mathematics is important as well. So this basically covers the fifth module in which we talked about linear regression, a little bit about gradient descent. We didn't talk about maximum likelihood estimation per se, but yeah, we did touch on it in the form of gradient descent and derivation and everything. So yeah, so this covers the very basic of linear regression and regression as a whole. So after that, we'll see a little bit on another models, k-nearest neighbor and naive Bayes model, which are probabilistic kind of model. One of them is probabilistic, another one is yeah. Well, let's discuss it again in the next module.